Hello and welcome back to a new chapter. This chapter is intended for you to understand what are capacitors, how they work, what they are made of, and we will build some circuits with them so that you can see them in action. But this doesn't mean that in other chapters we won't use capacitors. They are always needed almost everywhere. So in this course we will begin with a little introduction, then we will talk about the symbol of capacitor in a schematic, since capacitors can be divided into two big categories. Then we will see how the size of a capacitor is related to its capacitance. We will see briefly how a capacitor is made, how a capacitor works, and last but not least we will do a little practical experiment. So let's get started. Alright, so capacitor is not a very complex component. It has only two legs, and along with resistors and inductors, they are one of the most fundamental passive components that we use. You would have to look very hard to find a circuit which didn't have a capacitor in it. What makes capacitors special is their ability to store energy. They are like a fully charged electric battery. Caps, as we usually refer to them, have all sorts of critical applications in circuits. Common applications include like local energy storage, voltage spike suppression, complex signal filtering, circuits that we will learn and study about in the future courses. There are two ways to draw a capacitor in a schematic. They always have two terminals, which go on to connect to the rest of the circuit. The capacitor symbol consists of two parallel lines, which are either flat or curved. Both lines should be parallel to each other, close but not touching. It's hard to describe, it's easier to just show here. The symbol with the curved line indicates that the capacitor is polarized, meaning it's probably an electrolytic capacitor. We will study about these two types of capacitor in more detail in the next course, but for now what you have to know is that each capacitor should be accompanied by a name, like C1, C2, etc., and the value. The value should indicate the capacitance of the capacitor, like how many farads it has. As you can see in these two images, this capacitor with black and white band is an electrolytic capacitor, meaning that it is polarized. Polarized means that you can't connect the capacitor's leg randomly in the circuit. The plus sign should always be towards the more positive part of the circuit. In case you reverse the two legs, you will literally blow out the capacitor, and we don't want that, right? The non-electrolytic capacitor on the other hand is not polarized, so you can connect the two legs in whatever order you want. Anyway, more on this later. So when you're holding an electrolytic capacitor in your hand, you can notice two values written on the capacitor. The first one is the value of the capacitance, which is measured in farads, and the next value is the voltage, which is the maximum voltage the capacitor can handle. So if this electrolytic capacitor would be placed here in the circuit, and the input voltage V in would be more than 35 volts, the capacitor would blow up because it could not handle the voltage measured across its two legs. Electrolytic capacitors most of the time have capacitances in the range of microfarads, and speaking of farads, not all capacitors are created equal. Each capacitor is built to have a specific amount of capacitance. The capacitance of a capacitor tells you how much charge it can store. More capacitance means more capacities to store energy. I guess it makes sense. So the standard unit of capacitance is called the farad, which is abbreviated as F. It turns out that a farad is a lot of capacitance. Even 0.001 farad is a big capacitor. Usually you will see capacitor rated in the pico, nano to microfarad range. When you get into farad to kilofarad range of capacitance, you start talking about special capacitors called as super or ultra capacitors. The schematic symbol for a capacitor actually closely resembles how it's made. So a capacitor is created out of two metal plates and an insulating material called as dielectric. The metal plates are placed very close to each other, in parallel, of course, but the dielectric sits between them to make sure they don't touch. The dielectric can be made out of all sorts of insulating materials like paper, glass, rubber, ceramic, plastic, or anything that will impede the flow of current. On the other hand, the two plates are made of a conductive material that can be anything like aluminum, tantalum, silver, or other metals. They are each connected to a terminal wire, which is what eventually connects to the rest of the circuit. The capacitance of a capacitor depends on how it's constructed, so more capacitance requires a larger capacitor. This can be deduced also from this equation here, where the capacitance is equal to the relative permittivity times the amount of area the plates overlap, divided by 4 times P times the distance between the plates. Of course, you don't have to memorize this equation, it's just nice to know that it exists. Alright, so how does a capacitor work exactly? Well, as we know, electric current is the flow of electric charge, right? Which is what electrical components harness to light up or spin or do whatever they do. When current flows into a capacitor, the charges get stuck on the plates because they can't get past the insulating dielectric. So the electrons, which are the negatively charged particles, are sucked into one of the plates and it becomes overall negatively charged. The large mass of negative charges on one plate pushes away like charges on the other plate, making it positively charged. And the positive and negative charges on each of these plates attract each other because that's what opposite charges do. But with the dielectric sitting between them, as much as they want to come together, the charges will forever be stuck on the plate until they have somewhere else to go. And the stationary charges on these plates create an electric field, which influence electric potential energy and voltage. So when charges group together on a capacitor like here, the capacitor is storing electric energy just as a battery might store chemical energy. So again, when positive and negative charges group together on a capacitor plates, the capacitor becomes charged. And a capacitor can retain its electric field, which means hold its charge, because the positive and negative charges on each of the plates attract each other but never reach each other. At some point, the capacitor plates will be so full of charges that they just can't accept anymore. There are enough negative charges on the plate that they can repel any others that try to join. This is where the capacitance, which is measured in farads, of a capacitor comes into play, which tells you the maximum amount of charge the capacitor can store. If a path in the circuit is created which allows the charges to find another path to each other, they will leave the capacitor and it will discharge. So for example, in the circuit below, a battery can be used to induce an electric potential across the capacitor. This will cause equal but opposite charges to build up on each of the plates until they are so full they repel any more current from flowing. An LED placed in series with the capacitor could provide a path for the current, and the energy stored in the capacitor could be used to briefly illuminate the LED. Nice, right? Now let's try to see what happens if we build the previous circuit in our simulator. Unfortunately, capacitors have a built-in resistance that we will talk more about this in the next course. So an ideal capacitor is just a capacitor, but in the real world the capacitor has a resistance in series with it and even a little tiny inductance. The point that I wanted to make here is that even though the capacitor has naturally a resistance inside of it, that resistance is very small, sometimes negligible, sometimes not. So when I hit the switch, DC current will pass the capacitor until it's fully charged, right? And in order to not create a short circuit in that time period when the capacitor is charging up, we have a resistor here to limit the current. So I will hit the switch and notice how the current, which is yellow in this case, is decreasing from a high value until no more current is passing through it because it's fully charged. On the other hand, notice how the voltage across the capacitor has increased nicely to 5 volts, which is the voltage of the battery. Now if I hit the switch again, all the electric charge that the capacitor has stored will be released by the help of this path, which will bright up the LED for a little bit.